Hi everyone and welcome back to the channel. This is a question from the Balkan Mathematical Olympiad in 2009, hosted by Serbia. Pause the video if you want to give this problem a go, and when you're ready, we'll go through the solution. To begin, we can think about this equation modulo 4. So 3 can be written as -1, 5 can be written as 1, and any number squared will always be 0 or 1 modulo 4. And -1 to the x will always be plus or minus 1 depending on the parity of x, and 1 to the y will always be 1. Therefore this can only be true when it's 1 minus 1 is congruent to 0 mod 4. And therefore we know that x and z must both be even. Now if we let x equal 2x prime and sub this back into our original equation, we have the following, and we can rearrange to write 5 to the y as the difference of two squares, which allows us to factorize this as 3 to the x prime plus z and 3 to the x prime minus z. And given that the left side of this expression is a power of 5, then we know both these brackets must also be a power of 5. So we can say that 3 to the x prime plus z is 5 to the a, and 3 to the x prime minus z is 5 to the b, where a and b will be non-negative integers and a will be bigger than b. It's also clear that we can write 5 to the y as 5 to the a plus b, and therefore y is equal to a plus b. Now, if we consider what happens when we add these two equations together, then we have 2 times 3 to the x prime is equal to 5 to the a plus 5 to the b. But notice that when a and b are integers bigger than 1, the right side will always be divisible by 5, but that contradicts the left side. And therefore, since a is bigger than b, we must choose b to be 0. And so we have 2 times 3 to the x prime is 5 to the a plus 1. Now one immediate solution from here is when x prime equals 1 and a is equal to 1. This gives the value of x equaling 2 and y, which is a plus b, equaling 1. And if we sub these back into our original equation, we show that z is also equal to 2. And therefore we found at least one solution for x, y, z, namely 2, 1, 2. There will be another solution when x prime and a are both 0, but that would produce x equal to 0 and y equal to 0, and since the question has told us to deal with positive integers, we can ignore those. Next we can consider all solutions for x prime greater than or equal to 2, and since that will make 3 to the x prime a multiple of 9, we can consider this equation modulo 9. So this would be saying that 0 is congruent to 5 to the a plus 1 mod 9, and so 5 to the a is congruent to minus 1 mod 9. At this point we can just start plugging in some values for a, and we can find that a will be any number from the sequence 3, 9, 15, 21 and so on. And so we can represent it as 6n plus 3, where n will be an integer greater than or equal to 0. And factorizing this, we can write this as 3 times 2n plus 1. Now, if we sub this back into our top equation, we have that 2 times 3 to the x prime is 125 to the power of 2n plus 1 plus 1. And once more, we can use modulo arithmetic to help us here, since if we look at the right hand side modulo 7, then 125 is congruent to minus 1, and so the right side can be written as minus 1 to the power of 2n plus 1 plus 1. And since minus 1 to any odd power will always be minus 1, this entire expression is minus 1 plus 1, or 0 mod 7. But now consider what we've just discovered. We're saying now that 2 times 3 to the x prime will be some multiple of 7. But the left side only has factors of 2 and 3, and so this can never be divisible by 7, and thus no solution exists when x prime is bigger than or equal to 2. And therefore the only positive integer solution for x, y, z will be 2, 1, 2. And so we're done.